Welcome to In 5 Minutes. Let us discuss the second method of SSB-SC generation, which is called phase shift method. Now, problem that we face in the filter method is the use of filter itself. Because we require filter to suppress one of the two sidebands, and because there's a need to design filter at high frequency, we have to go for that modified filter method in which we first generate DSB signal at low frequency, but it can't be very low again. It has to be a frequency which is outside the range of modulating frequencies. So the problem of filter design is simplified in the modified diagram, but it is not completely gone. It will only be completely gone if I don't have to use filter in the generation of SSB. That means I should be able to suppress one of the two sidebands without using filtering operation. And this is possible if we go for the second method, which is called phase shift method. So the very first thing that you should keep in your mind is that the phase shift method will not use filter anywhere to suppress one of the two sidebands. The question now is how it suppresses the other sideband in that case. So let us discuss the block diagram first, and then we will do a small mathematical analysis which will prove that one of the two sidebands are suppressed and only the other sideband comes at the output side. The input is nothing but the modulating signal which goes through the audio amplifier so that it is amplified and then given to the rest of the circuit. You can see we have a carrier source which will generate single carrier frequency. It will be the final frequency FC. We are using two balance modulators. The second balance modulator in this case is taking the original carrier as it is, but the first balance modulator will take the 90-degree phase shifted version of the carrier. So carrier is 90-degree phase shifted and then given to the first balance modulator. Not just that the carrier is 90-degree phase shifted, you can see that the modulating signal is given as it is to the first balance modulator, but when it goes to the second balance modulator, it is 90-degree phase shifted. By now, you should have understood very well that balance modulator always acts as a multiplier. When the two inputs are carrier and the modulating signal, then output of the balance modulator is always double sideband suppressed carrier signal. Let us quickly write down what are the inputs to both the balance modulators. To the first balance modulator, the AF signal goes as it is. Let me write the AF signal or the modulating signal as cos 2 pi FMT. Now, just to simplify the expressions, we will replace 2 pi FM with omega m, and 2 pi FC. FC is the carrier frequency in hertz. We will replace 2 pi FC with omega c. Omega is the frequency in radians per second. So to the first balance modulator, the input is cos omega mt. Now the same cos omega mt, when it goes through the 90-degree phase shifter, you can see 90-degree phase shifter, the output will be sine omega mt. Right now we are taking modulating signal with only one modulating frequency. In practice, it will contain all the frequencies from 20 Hz to 20 kHz, and hence it will not have to phase shift only the single frequency. It will have to phase shift a band of frequencies from 20 Hz to 20 kHz, and hence the phase shifter that we need in this case is called wide band phase shifter. Now, instead of writing sine omega mt, I can simply write it as cos omega mt plus 90, because ultimately we are providing 90-degree phase shift